Hey class, so before we jump into calculation of temporal moments, there's one more step we need to do to prepare our data, and that is to normalize the breakthrough curve. So in this quick video, I'll show you what I mean by that and how to do it and how to check your work. So the reason that we're going to normalize a breakthrough curve is I want you to envision that you went out to a field site, you chose some amount of mass to do your tracer release, and you got this data set back. Now let's envision that someone else went out, right with you or that morning, but they chose a different mass. And if they chose less mass, what they ought to get back is something that looks like about the same shape that you got, but its magnitudes are going to be really different. And even though you measured the same system, the fact that you chose to do it with different masses is going to yield different results for you. And so this is a problem. It limits our ability to compare between experiments or find metrics that are a fair way to assess really heterogeneous systems, or your same system under different discharge conditions. So the way that we address this problem is by normalizing the breakthrough curve. So we turn it from a time series of concentrations into a normalized time series, and this y-axis on the normalized time series actually represents the probability. And you can see I've written in orange there. The height of this normalized curve at any location represents the probability mass released at time 0 when you injected leaves at time t1, for example. So what we're doing is turning our data from a concentration time series actually into a probability distribution, or a probability density function, or a PDF, people like to call these. So let me show you how. What we're, and for both experiments, if we've done everything correct, these curves should end up matching up at the end of the day. So this means our results are not sensitive to our experimental design. This is what our goal was. Now let's look at how we do it. So to calculate our normalized concentration, we're going to take each concentration that we observed up in the numerator, and we're going to divide it by the area under the curve. So up in the numerator will be each individual observation, and down in the denominator will be the area underneath your observational curve. Right? And so what you're doing is asking, for this concentration, what fraction of the total signal does it happen to represent? And that area underneath the curve you might envision like this area underneath the concentration time series that was on the top of the previous slide. This normalized concentration, this is the time series that we're going to use to calculate our temporal moments. So in the next video, where I show you how to do the temporal moment calculation and what they are, every time I'm talking about concentration there, it's important that you know I'm talking about the normalized concentration time series. If you skip the normalization, you're going to get results that are not comparable to other experiments or other systems. Finally, there's an easy way to check your work. If you have done your normalization correctly, the area underneath that curve should equal 1. So in other words, if you go ahead and plot normalized concentrations through time, the integral of the area under this curve should be equal to 1. Another quick check that you might consider, if this is a probability distribution, this peak value should be less than 1. So you shouldn't have any values that are greater than 1 if you've done this normalization correctly. Okay, so I hope this helps you see how you can normalize a breakthrough curve and why you might do it. And this is a requisite step in your data set before you go on to calculate temporal moments. In the next video, we'll look at what a temporal moment is and how to do it. Thanks, everyone.